Periodic table patterns. Starter. What are the differences between groups and periods on the periodic table? Explain your answer. There are 18 groups on the periodic table. Groups have similar chemical properties, numbers of valence electrons, and increasing atomic mass as you go down. So if we look at group 1, all these elements are going to have similar chemical properties, and their atomic mass increases as you go down. This is group 1, group 2, group 13, they all have 3 valence electrons, group 14 with 4 valence electrons, group 15, 5, group 16, 6, group 17, 7, group 18, 8. There are 7 periods on the periodic table. So this number represents a period. This tells you how many energy levels go around the nucleus. So in period 1, you have hydrogen and helium with 1 energy level. Period 2, you would have lithium, beryllium, boron, carbon, etc. Period 3, they go horizontally. Period 4, period 5, period 6, period 7. Periods and energy levels. Shells. Let's draw the energy levels for hydrogen, lithium, sodium, and rubidium. Elements in the same period have the same number of energy levels or shells. So if you're in period 1, you have 1 energy level around your nucleus. If you're in period 2, you're going to have 2 energy levels around your nucleus. In period 3, you're going to have 1, 2, 3 energy levels around your nucleus. If you're in period 7, you're going to have 1, 2, 3, 4, 5, 6, 7 energy levels around your nucleus. Let's look at groups and valence electrons. Elements in the same group have similar chemical properties. So if we look at group 1, they all have 1 valence electron in their outer shell. That means they all react similarly. They have 1 valence electron, they need 8, so they're going to try to get 7 more. In group 2, all these elements up and down have 2 valence electrons in their outer shell. They want 8, so they're going to try to get 6 more. We skip these groups in the middle, and we come to group 13, and you look at the second digit. All these elements have 3 valence electrons. They need 5 more. Group 14, they all have 4 valence electrons. They need 4 more. Group 15, 5 valence electrons. Group 16, 6 valence electrons. Group 17, 7. When you get to group 18, they have 8 valence electrons in their outer shell. It's full, so they're chemically stable. They're called the noble gases. So let's look. If you're in group 1, that means you have 1 valence electron in your outer shell. If you're in group 2, you have 2 valence electrons in your outer shell. If you're in group 13, you're going to have 3 valence electrons in your outer shell. Group 14, you're going to have 4. 1, 2, 3, 4. And group 18, 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. Let's practice. The structure of an atom, the electron cloud, and energy levels. Surrounding the nucleus is an area called the electron cloud or energy shells. Inside the electron cloud, negative electrons orbit around on different energy levels. The electrons are so small that they basically have no mass, so they're not included in finding the atomic mass. As a general rule, each energy level only holds so many electrons at a given time. The first energy level, which is closest to the nucleus, can only hold 2 electrons. The second energy level can hold up to 8 electrons. The third energy level may hold 8 or more electrons. Structure of the atom, the electron cloud, and energy levels. Valence electrons. The number of electrons in an atom's outermost energy level are called valence electrons. The periodic table has numbered columns called groups. Elements within these groups are families and have similar properties. These electrons are important because they determine how reactive an element is with other elements. For example, lithium has only one valence electron in its outer energy level. Since the second energy level may hold up to 8 electrons, lithium would need 7 additional electrons in order to fill its outermost energy level. But it's easier for lithium to give away 1 electron instead of finding 7. Lithium is highly reactive. So we could also say lithium is in group 1. All these elements have 1 valence electron. So they are all highly reactive. They all want to give away that 1 valence electron. Let's drag and drop the descriptor boxes besides the correct table in the image. So let's look. These elements are non-lustrous, poor conductors, brittle, and are not magnetic. Many are gases. So these would be your non-metals. Your non-metals are located to the right side of that zigzag staircase. So I can drag and drop this descriptor next to that image. Let's have a look at this descriptor. It reads, these elements are lustrous, conductive, malleable, ductile, and can be magnetic. These would be your metals. Your metals are found to the left of the zigzag line on the periodic table. And lastly, these elements will share properties of metals and non-metals. So those would be your metalloids that are found directly on that zigzag staircase. Let's drag and drop the descriptors. All elements found here have the same number of energy levels. So energy levels, those are going to be periods. Periods run horizontally. Those tell you how many energy levels or shells to put around the nucleus. These elements are extremely reactive because they want to get rid of their 1 valence electron. So those would be elements in group 1 who have 1 valence electron. And lastly, these elements are called noble gases and are least reactive because they have an outer shell that's full of 8 valence electrons.
When you're traveling somewhere new, chances are you're going to use a map. Maps come in all forms. Some are colorful with little pictures, some have ways of showing different altitudes, and some have the sole purpose of showing state or national boundaries. Either way, just like the spot on a map can tell you information about that location, the position of an element on a periodic table can help you predict some of the element's properties. An element is a pure substance, made up of only one type of atom. Elements are the building blocks of all matter, just like the letters are the building blocks of all words. There are currently 118 known elements represented on the periodic table. Some are found in nature, and others are created in laboratories. Each little block on the periodic table represents one element. Some examples of elements are gold, oxygen, neon, potassium, and tungsten. Each different element has atoms with a different and unique number of protons. This is called the atomic number. Because there are so many elements, there needs to be a system of organizing them. This is where a Russian chemist by the name of Dmitry Mendeleev comes in. In the late 1800s, when only 60 or so elements had been discovered, Mendeleev decided to arrange the elements in order of increasing atomic weight. While doing this, he also organized them so elements with similar characteristics were grouped together. In doing this, it was necessary to leave some blank areas in his organization, which later ended up being spots for elements that hadn't been discovered yet. What this means is his system of organization worked out so well that he could predict both the weights and the properties of undiscovered elements. We are still using this organization today in the periodic table. However, elements are currently organized in order of increasing atomic number. As Mendeleev was arranging the elements in order of increasing atomic weight, he noticed that patterns repeated periodically. Each time a pattern started over, he started a new row. A period on the periodic table is really just a horizontal row. The current periodic table has 7 periods, with an island of 2 periods down below. Why is that little island down there? It's really just because if those 2 rows were put into the periodic table where they belong, the table would take up so much space and not easily fit onto a piece of paper. You know how sometimes Alaska gets put into a different location on a map of the United States. Alaska is not really found below California, it's just there to save space. So when you're using the periodic table, just keep in mind where they should belong. The top row of that island is in the 6th period, and the bottom row is in the 7th period. Also, you may find that some periodic tables do show these 2 rows in their correct location. The vertical columns on the periodic table are called groups or families. Groups probably come in most handy when predicting the properties of an element. Just like people in a family all may share similar traits, elements in the same group on a periodic table also will have similar properties. The groups are numbered from 1 to 18, from left to right, and some of the groups
So let's use the information on the periodic table to fill in the boxes by looking at the Bohr model. So number of protons. So here this image is telling me I have positive protons here, but it's a little difficult for me to count those protons. But I know the number of protons equals electrons. So if I count my electrons, I should have my number of protons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 protons, so I have 11 electrons. By counting my electrons equal my number of protons, so they're the same. So now I can go to my periodic table and I can identify this element through the number of protons. So I'm looking for an element whose atomic number is 11, and sodium's atomic number is 11. Okay, I can also look at my periodic table to determine my number of neutrons of sodium. So here's sodium. I want to find how many neutrons, so I want to take that mass number and subtract my atomic number. So 23 subtract 11 will give me 12 neutrons. So I can go back to my periodic table, and my number of neutrons is 12. My group number. My group number I can find above the vertical column. So going back to my periodic table, here is sodium. So sodium's group number is number 1. So all these elements have 1 valence electron, including sodium. So I can go back to my periodic table, and my group number is number 1. So I have 1 valence electron. So again, here I have one valence electron, and that's indicated by my group number. For my period, I would count how many energy levels I have. 1, 2, 3. So I should be in period 3. So let's check that by going to the periodic table, and here's sodium in group 3. So all these elements would have 1, 2, 3 energy levels around its nucleus. Okay, let's go to our next Bohr model. So again, we can do the same. So I want to know how many protons and electrons I have. So again, I could count these protons, but just to be sure, I'm going to count my electrons because I know my protons equal electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I have 9 electrons. So my number of protons is 9, which makes my atomic number 9. So I can go to my periodic table and identify this element because your number of protons identify the element. So periodic table, and here's my atomic number 9. So I'm looking at fluorine. And my number of neutrons, I can calculate that by looking at my atomic number. My mass number, subtract my atomic number. So your mass number rounded would be 19. So mass number subtract atomic number would give me 10 protons. Or 10 neutrons. My group number would be the number above the symbol. So here, my group number is 17, so it means I have 7 valence electrons. So group number is group 17 with 7 valence electrons, meaning I just need one more to have my shell fall and become stable. I could even check, do I have 7? 1, 2, 3, 4, 5, 6, 7. 7 valence electrons in the outer shell. My period number is how many energy shells I have around my nucleus. I have 1, 2. So I should be in period 2, and I can just check that. So here's period 2, and I have fluorine. Okay, and let's do one more. And so let's do the same thing. I can't count all those little blue protons, so I know my protons equal my electrons, so I'm going to count those. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 electrons. My number of electrons equal my protons. By looking at my protons, I can identify the element. So I can go to the periodic table and see whose atomic number is 13. Your atomic number 13, we're looking at aluminum. How many neutrons does aluminum have? I have to take that mass number, which is my rounded number. So 26.9 rounds to 27. 27 subtract your atomic number 13. So 27 subtract 13 is 14. So my number of neutrons is 14. My group number is the number above my column, so group number 13, meaning I have 3 valence electrons. Group number 13 with 3 valence electrons. 1, 2, 3 valence electrons in my outer shell. My period would be how many energy shells I have. This would be 1, 2, 3. So let's see if aluminum is in period 3. Yes, aluminum is in period 3 with 3 energy levels around its nucleus. All right, And let's have a look at our connection. Which atom model is least likely to react? Remember, atoms that are least likely to react are going to have a full shell in their outer energy shell. So I want 8 valence electrons in my shell to be stable, unreactive. So I'm going to count how many valence electrons we have here. 1, 2, 3, 4, 5, 6. This has 6. 1, 2, 3 valence electrons here. 1, 2, 3, 4, 5, 6, 7, 8. So this atom 3, has 8 valence electrons. It's going to be the least likely to react because its shell is full. And let's count here. 1, 2, 3, 4, 5, 6. Okay, so all these other atoms are going to be reactive to try to get 8. But when the atom has 8, it is full, it's stable, unreactive. And one more connection. The periodic table is organized into groups and periods of elements. The characteristics of a certain group of elements are listed below. The element is shiny, it's solid at room temperature, has atoms with 2 valence electrons. So this is a clue here. If I have 2 valence electrons, it means I'm in group 2. So which of these elements is in this group? So I'm going to go to my periodic table and see what elements are in group 2. So here I have group 2, so all these elements have 2 valence electrons. So going back to my answer choices, strontium, let me see if that is correct. It's in group 2, so I can circle that answer. Okay, and then for our exit, which element has similar properties to sodium but has a greater atomic mass? Now remember, similar properties mean you are in the same group because you have similar chemical properties. So potassium would be in the same group as sodium, and potassium also has a greater atomic mass than sodium.